This lecture is going to be about data classification and presentation. We are just going to talk about two things in this lecture. First being the different scales of measurement. Second being the application of tables and graphs, meaning how do we use tables and graphs to present our data. Now, scales of measurement. The basic message here is the idea that all data is not alike. Or in other words, different kind of data require different methods in terms of collecting them or in terms of their statistical analysis, as well as how you present the data eventually. Now, there are three common scales in which we use for the three different scales of measurements, and the first is nominal data, then there's ordinal, and then there's numerical, and we'll look at each of them. Now, nominal scales are the first type, and you can call it the simplest level of measurement. And the basic way of describing it is this is category type data, where the kind of data you collect can be summarized in terms of categories. For example, yes and no, or let's say you're doing a survey, you're collecting the race of the participants, and they are I am a Malay, I'm a Chinese, I'm an Indian, and when you collect the data, you say, oh, I have surveyed about 100 people, and there are 60 Malays, there are 30 Chinese, and there are 10 Indians, and so on and so forth. In the medical field, they might be benign and malignant, or perhaps male, female, other. So these are examples of nominal scale type data. Now, just a quick mention here. For special kind of data where there are only two observations, yes, no is the good example here, or maybe just male, female, no other. These kind of data is known as binary observations, where there are only two possibilities. Binary meaning, the word binary here meaning two. Now, these are still nominal type data, but they're just given a special name, binary observations, where there are only two possibilities. Now, nominal scale type data has another name. Some people call it qualitative observations, where they describe a quality of the person being studied. Now, quality here doesn't mean high quality, low quality. Quality here means like the characteristic or the property of a particular object or a particular person. For example, you might be describing a person, say this person has the excellent quality of courage, for example. Now, I'll just say here that although this is what the textbooks do say, I will say that it tends to make things a little bit confusing when you try to mix up nominal and qualitative. I prefer to think of them as two separate kind of descriptions. There's nominal type of data, and much nominal data also happen to be qualitative type data. When we look at the counterpart of qualitative later, it will become clearer. But in this case, I would say that qualitative, you can think of it as a kind of data which is not purely scientifically measurable, and there's always a bit of human element inside. Now, what do I mean by that? If we go back to the previous example, the one about race, remember the Malay, Chinese, Indian? Now, what happens when you're trying to, what happens when you come across a person who is of mixed race? Now, how do you categorize him or her? From there, we've discovered that race is actually something that is actually colored by human culture or human opinion. It's subjective. It's not something that is objective. It's not something that is purely scientifically measurable. The only way to do that would be some kind of gene testing or some DNA thing, and that wouldn't be a nominal scale anymore. So in this sense, you can think of qualitative as separate from nominal scales, but again, you might still see it mentioned in some textbooks where these two are equal to be the same thing. Now, as mentioned just now, nominal scales also are called categorical observations for obvious reasons. Now, after we collect the data, how do we describe it? A common way is in terms of percentages. For example, 5% of all cars found on the road in Kuala Lumpur are from Toyota. Or proportions, 3 out of 10 people in Kuala Lumpur are Chinese, for example. Now, how do you present this data? Usually we use contingency tables as well as bar charts, and we'll look at that later. Now, the second type of measurement that we're looking at is ordinal type scales. This is also categorical data, just like nominal data just now, but the data possesses an inherent order. There's an order to them. Now the best way is to look by example. The risk factors 1, 2, 3, 4, 5, category 1, category 2, category 3, category 4, category 5. Now for medical physics, when we're doing image quality optimization for x-rays, for example, we may do some kind of survey form, and we ask the people to rate what's the image quality 1, 2, 3, 4, 5. Outside the medical field, customer satisfaction forms, customer satisfaction from 1 to 10. Age groups below 12, below 18, below 30, below 40, below 50, and so on and so forth. Now, one thing I'd like to point out is that, remember previously I said about nominal data being also known as qualitative data because they have there's a human subjective quality to it. Now the same thing you will see inside these ordinal scales, particularly for these three. I'll talk about the fourth one in a moment. Now these three risk factors, image quality, customer satisfaction, once again, there's nothing purely scientific, precisely scientifically measurable about them. There is a touch of human subjectivity to them. Now, age group, if you've noticed, is something that you can measure scientifically, but the way we group them is based on our need. Alright. Now, if they are not grouped, if they were based on purely by age, my age is 12, my age is 13, my age is not between 12 to 18 in this group, for example, it wouldn't be an ordinal scale anymore. It would be the next category, which is the numerical one. Now, another thing which I would like to point out is that for ordinal scales, the difference between the two adjacent categories is not necessarily equal. Now, this is very important to keep in mind. It's most obviously seen here, where the difference between the age groups of the difference between the size, let's call it, or the gap between the first age group and the second age group and the third age group and the fourth age group and so on is not necessarily the same. For example, the average difference between these two is probably about 10 years, but the average difference between these two is more like 12, and this one is more like 6. Now, the same thing applies in, say, risk factors 1 to 5 or image quality 1 to 5. The difference between image quality 1 and image quality 2 is not necessarily twice as good, or between 1 to 5 is not necessarily 5 times as good. There's no way to actually measure it because this is not really, as said, these are not really qualitative or scientifically precise measurements. These are subjective or these are not numerically precise quantitative type measurements. These are more human subjective qualitative type measurements. Now this brings us to the third type, the numerical scale, also known as the quantitative observation. Now for most people, this is kind of like the gold standard of scientific data, meaning that as far as you can, try to collect your data in the numerical scale, or in other words, in the quantitative observation. Now what does this mean? It means we're measuring the quantity of something. Doesn't seem very helpful. Let's put it another way. This is something which is not subjective, not a subjective measurement, meaning it's not based on any kind of human factor. Now common examples here would be for example, let's say the weight or the height of someone. This is based on an objective measurement. It's not based on me guesstimating it. It's based on physical measurements. This is in contrast to the previous qualitative measurements where there's also a human factor involved. Now in numerical scales, there's two subcategories. One is the continuous type and one is the discrete type scales. Now for continuous scales, these are measurements where the thing you're measuring is continuous. Or in other words, there is, in theory, infinite precision involved. Now, in practice, when we actually measure it, we always round it out because there's no way to get infinite precision, of course. But in theory, you could always get more precise measurements if it were scientifically or financially feasible. Now, example, age in years. Usually, I say I am, for example, 30 years old, for example. I'm not. But I could also give my age in months. That would be a more precise measurement. I could also give my age in days. I could give my age in hours. I could give my age in seconds, and so on and so forth. I could go to, in theory, virtually infinite precision. Now the same thing applies for other physical measurements, for example, weight and time. And that's the continuous kind of numerical data. Then there's the discrete kind of numerical data, where data is only possible in integers. Integers meaning round numbers, numbers with no decimal points, 1, 2, 3, 4, 5, and so on. Examples like that might be how many children do you have, what are the number of days in the year, how many previous operations has this patient had, and so on and so forth. So it's only possible in integers. You can't have had 3.5 operations done, for example. However, they are still numerical scales in the sense that they are scientifically measurable. There's a good definition for what we're actually measuring, and there's no kind of human element, there's no kind of human subjectivity involved. Now that's it for the different kinds of data. Now after we collect these data, depending on the different kinds, how then do we present them? Now for nominal and ordinal type data, we tend to use tables. In this case, frequency tables, where the category is in one column and the frequency, also known as the count or the percentage, is in the other. Now this is the raw data. This is, let's say you're collecting a bunch of patients where you take their blood and you send them for a lab test. And here bacteremia here just means that whether there's a presence of any bacteria in the blood, yes or no, and if there is, what kind of culture you got, what kind of culture of bacteria, what bacteria was cultured from it. So this is the raw data. I collected 1 patient, 2 patient, 3 patient, 4 patient, 5, 6, 7, 8. Now obviously this is nominal type data. For example, this is binary type, where there's yes or no, is there presence of bacteria in the blood, as well as what kind of culture. This is a bunch of groups inside here. There's no growth not done, S. aureus, S. epidermidis. Sorry, I might not be pronouncing them correctly. So how do we properly present them? We use frequency tables. For example, this is an example of a frequency table that only looks at the bacteremia. How many number of patients had bacteria in the blood? How many patients did not? How many patients resulted in no culture, no growth, or this particular culture, and so on and so forth. Right? Now the problem with doing it this way is, of course, you kind of like break the relationship between these two data, the bacteremia and the culture. They are related because some of these patients here actually, the patients here are exactly the same patients here, and there's a relationship between the two. And if you put them in two separate tables, you kind of lose that relationship. So there's another way you can do it, and that is by using contingency tables. It's for examining 2 or more characteristics, and these tables then become multi-dimensional. Now, there's nothing earth-shattering about this. I'm sure many of you have used contingency tables before. Perhaps this is just learning the technical term for them. Once again, this is the raw data, and as mentioned, there is a relationship between these variables. So this would be a way of doing a contingency table while still maintaining a relationship. So if you notice, there's multi-dimensions. There's the first dimension, there's the second dimension, and then there is the frequency or the number. So there were patients who had bacteremia and no culture, 0. And no bacteremia, no culture, 1. Bacteremia, no growth, 1. No bacteria, no growth, 2. And so on and so forth. And this is one way to do it. You could do it horizontally. You could also do it vertically, flowing down for obvious reasons. And there is a much more efficient way to also tabulate this kind of data, and that's by doing it this way, where you put one of the dimensions here or one of the factors here and the other factor, or one of the variables here and the other variable here, and the center is kind of like the cross of them. So this particular cell here is the number of patients who were bacteremic and no culture, which obviously is 0, and non-bacteremic, no culture, 1. Bacteremic with S. aureus here is 1. Non-bacteremic with S. aureus obviously is 0, and so on and so forth. Now, that was by using tables, and I'll be honest here, my personal preference is to use tables. However, in some cases, graphs are more useful. I'll just quickly mention, the reason I prefer tables is I find that they are more information dense, meaning that there's a lot more information you can put inside tables, whereas if you try to put the same kind of information inside visual displays like graphs, things can tend to get a bit cluttered. However, there are certain graphs which are very good, and we'll talk about them later. For now, we talk about the basic ones. The bar charts. I'm sure everyone has seen this before. Categories in the x-axis, counts of percentages in the y-axis. So again, counts, frequencies, percentages. I'm sure everyone knows how to convert between the two. I mean, percentages is just the counts divided by the total, right? So here's a simple example of, again, nominal data. This one is in terms of race. I'm sure everyone has seen an example of these kind of bar charts before. Pie charts, the second type. Pie charts are similar to bar charts, except they're mainly used when you want to emphasize proportions rather than proportions or percentages, where you don't want to see the absolute numbers. You want to see how many percentage they are. Each particular one is compared to the rest of the whole. So it's the same kind of data just now, except now seen in terms of a pie chart. Now, again, I like to mention here that I don't really like these kind of graphs because I think they use up a lot of space, and this could actually be summarized in a tiny little table. And to be honest, if you were, let's say, trying to compare between the racial percentage breakdown among different states in Malaysia, if you're using a pie chart, you have one pie chart here for the Selangor, another pie chart here for Johor, another pie chart here for Penang, another pie chart here for Sabah, another pie chart here for Sarawak, and it gets unwieldy really, really fast. People look through the entire thing and they get totally confused. So I tend to prefer tables, just keep that in mind. Now, if we look at numerical type data, we also have a bunch of ways in which we present the data. First, some legacy ones, stem and leaf plots. I think many of you may have come across these before. We hardly see these nowadays. These were more used in the old days because of lack of computers and these kind of graphic user interface to design these tools. However, for historical sake, we just look at them. Stem and leaf plots. Now what they do is they arrange data in order, first digits on the left, subsequent digits on the right. And if you look closely, it looks very close to a bar chart. However, they are more powerful than bar charts, because the thing about bar charts is that you group up the data, but you lose the individual. You can't see the individual data once they get formed in the bar chart. They get lost inside that bar. Stem and leaf plots don't have that problem. You can actually reconstruct the raw data just by working it out. For example, what this thing here means is that this is actually made out of 10, 14, 14, 15, 17, 18, 19, and 19, which are some of the raw data inside here. Similar here, this is made out of 21, 23, 23, 23, 24, 28, 28. This is made out of 31, 31, 31, 32, 33, and so on and so on and so forth. You may have noticed that this doesn't really add up, and I'm sorry about that. But that's the idea here. The raw data inside here, you may present it semi-graphically in using the form of a stem and leaf plot. And once again, this has the similar benefit of a bar chart in the sense that there's a visual, you can see a visual overview of the kind of shape of the data, but you still retain each individual data values. Now, that was the stem and leaf plot. If we want to do tables, just like how we do it for nominal and ordinal data, I'm afraid that it's not really possible to do for numerical data, for the obvious reason is being that how do you actually group them? And so the answer is that you actually do have to group them. In other words, you force the numerical data to become ordinal data. You've taken the raw numerical values and you break them into groups. You group them up and you calculate the group. So once you turn numerical into ordinal, you do it just like what we showed just now. You make a normal frequency table. Nothing special about that in this case. Then it becomes very clear. Just one thing to note, be careful when you form these kind of groups. I didn't do it very well here. There's a better way to do them. I'll mention in a moment. But let's a very common mistake you see people do is like 25 to 30, 30 to 35, 35 to 40, and so on. And so the limits on each end become very ambiguous. You have a person who is 30 years old. Does he fit in the 25 to 30 or the 30 to 35? I don't know. Same thing here, 25 to 29. What I really mean here is 25 or larger and to less than 30, and it's 30 or larger to less than 35, and so on and so forth. One other thing to note, be careful about open-ended limits. You see some tables end up with something like larger than 75, and although it does make sense to do so, if you don't have the raw data, it's hard to know just larger than 75. Does that mean it goes up to 80? Does it mean there's a person there who's like 100 years old, and so on and so forth? Well, you just don't know. Now we're looking for the more graphical methods for numerical type data. Let's start with the most basic one, histograms. I'm sure you've seen them before. Now at a quick glance, they look exactly like what they are, which are bar charts. Right? They're basically bar charts. And once again, to create a bar chart, similar to the frequency table just now, your numerical data has to be turned into ordinal data or categorical data with an order. So you have to group them up. So similar to just now, you've broken that age into age groups, and now you make the bar charts. And the special thing about histograms is that there is no space in between each category. It forms a seamless whole. This is so you can see a shape, and also to emphasize the point that this is not actually categorical data, this is continuous data. A much more useful representation, however, I feel, is the box and whisker plot, and you will see this a lot in scientific literature as well. I believe this is probably one of the most useful methods for doing graphical presentations of numerical data. Now, what actually is a box and whisker plot? It is basically just this kind of thing. We don't actually see the data, like the shape of the data in terms of like that, like the histogram. Rather, you just get a summary of different summarizing measures of the data. We'll talk about those later. But for now, let's say you know the maximum value, the minimum value. You know something called the midpoint, the third quartile, and the first quartile, meaning the 25 percentile number, the 75 percentile number, and the 50th percentile number. It basically takes 5 values, and you plot 1 dot, 2 dot, 3 dot, 4 dot, 5 dot, and rather than just putting dots, you draw it in the form of a box with a dark line which blends the midpoint and the 2 edges. So this is the box and whisker plot. Now the good thing about this kind of plot is it gives you a quick, simple glance at the most important descriptions about the group of data which you collected. We'll talk about what is important here. For one thing, I can see what's the average value, I can see how far it ranges, and I can also, from here, once you get used to it, you can actually see the shape of this. Now the most important thing I can tell you about this is that it is skewed. This data is skewed. Now we'll talk later about why I know it's skewed, but the clue here is that this bar is not in the middle of the box. It's towards the, let's call it the left, for example. Now the other thing that's good about box and whisker plots is because it's just self-contained, a simple picture like this, it makes it very easy to compare different groups of data. For example, let's say I'm collecting age of men versus, not age, let's say I'm talking about life expectancy. So life expectancy of men versus life expectancy of women. So when I compare them, I can compare them easily with box and whisker plot because I can just position them right next to each other, and the same scale of the y-axis here allows them to be directly comparable. Of course, it would not be. It must be said that that box and whisker plot is not the only way to show any kind of comparisons. Another way is use of frequency polygons. Frequency polygons are basically identical to histograms. This is just like just now. However, unlike the histogram at the back, the frequency polygon is just a line graph. where each point on the line is the midpoint of where the histogram would be. Now, what is the benefit of using the frequency polygon compared to using a raw histogram? Which is, if I removed out the histogram here, it's just here for illustration, I could then overlay another frequency polygon over here. Now, similarly, let's say this was this is mainly for comparison purposes. For example, this is the age group of people in Petaling Jaya. There I could have another one. This is the age group profile of people in Klang, and there'll be another frequency polygon, again for comparison purposes. Now there's a special case here about visual or graphical methods when we have two characteristics or two separate pieces of data. Now, if I have nominal to nominal, I use contingency tables. We've seen that just now. Do you still remember the one about bacteremia and culture? There was actually two sets of data, both of them nominal type data, and you could squeeze them into a single table with, let's say, one dimension being the bacteremia, the other dimension being the culture. Now, if you have two data where one is nominal and one is numerical, it might surprise you, but we have actually seen it just now, and that was a box plot. Now, what did that mean? Now, do you still remember what I gave the example just now? It was, let's say, life expectancy. There was life expectancy for males and females. Now, I don't know if you noticed, but there were actually two variables there. One was life expectancy, and the other one was gender. Life expectancy is nominal, gender is numerical. So life expectancy was on the y-axis, and gender was on the x-axis. So that allowed me to put one box plot here, another box plot there, and so on. Now, however, what happens if your two characteristics or your two data variables are both numerical? For example, let's say height and weight. Then the only way to do that, to properly graphically represent them, is by using scatter plots. Now, scatter plots just mean that you have an x and a y axis, where one of your variables is in the x, one of the variables is in the y, and for each individual data that you have, you make it into a dot. So one dot here, one dot here, one dot here, one dot here, one dot here. And from there, the scatter, all these scatterings of the dots forms like the shape or the picture of your data. Now, it is considered the proper thing to do is usually to place the risk factor or the independent variable, or let's call it the causing variable, the variable that causes the y to be on the x, right? So the x-axis is the variable which causes the y-axis, and the y-axis is the dependent variable, or the variable that depends on the x-axis, or the one that the x-axis is causing. I wrote here saturation of bar and percentage, but perhaps a simpler example here would be age here and height here. So obviously you'd expect the height to cause, the age to cause the height. As you age, your height tends to increase. It doesn't make sense to put it the other way around. As your height increases, it will cause your age to increase. Now that doesn't make sense. Of course, this example doesn't scale all the way to 100 years old, but I think it gets the idea across. Now, after showing a quick run through of all the charts and the graphs that we can use, I'll just mention a couple of rules of thumb here. It's very hard to tell you what makes a good graph or a good chart, but in general, we should be simple, easily understood. There should be concise, complete labels and legends. Most important, it should present information in a concise, understandable way and not try to waste space. And most importantly, it should not be misleading. As in, the chart should tell you what the data actually means and not try to fool you into into something else. And so to end off this particular lecture, I'll just show a couple of examples of some common mistakes that happen when you try to present data. Now, here's an example of a table that's way too complex and too overwhelming. Just pause it for a moment, and you can take as long as you like to just study this particular table. This table is not really a frequency table or anything. It's just a statement of facts, but they made some attempt to try to group it to make it understandable. But I can tell you right now that there's a much better way to do this, and no matter how much you stare at this, it's going to take you a long time to even try to figure out what on earth this table is trying to present. What is the What is the takeaway message of this, and even what kind of conclusion can I come from all this? So, smoking policy survey. A survey of 245 facilities was taken to gauge the effectiveness of the smoking policies. So what's the conclusion? Was it effective or not? I don't know. I see 80%, I see 20%, They don't seem to be related to one another. So this is an example of a table that doesn't actually help. It just makes people more confused when they look at it. Now here's an example of a chart that tends to lead people to make bad interpretations. Now take a look at this chart. Now if you notice, there's a nice trend going up here, and if I were to ask you, what do you think would be the obvious headline for something like this? Here is a look at total retail sales. Now most people are going to think, ooh, retail sales have been steadily increasing. But, surprise, surprise, the actual headline is retail sales down. Now, why did they actually say that? It's because they were comparing April here to March. And compared to March, April has gone down. Or in other words, it's down by 0.2%. Wow. If they wanted to do that, they should just posted this little table inside here. Because if they are showing this kind of graph, the natural assumption most people would take is that retail sales are actually up, not down. Now let's look back at the previous graph, and we're going to illustrate a separate problem. And that's, if you quickly look at this graph, it looks like retail sales have been going up dramatically, basically building from nothing all the way to total. But if I told you that the difference here was actually 0.2% as well, you probably think that doesn't look like 0.2%. Now, why not? Turns out that this graph doesn't actually start from 0. It starts from 225 billion all the way to 270 billion. So if you were actually to scale this correctly from 0 all the way to 270, this trend here would look more like this tiny little blip here. And so all these things would be insignificant, they're lost to noise, but it puts things into their proper context. This is actually not a very significant number. Now the same thing happens here. Advertising, not surprising, more than 98% of all Chevrolet trucks sold in the last 10 years still on the road. Comparing Chevy to Ford to Toyota, reliability, wow, it looks like Chevy is so much higher than Ford, so much higher than Toyota, but if you look at the scale here, it's from 95 to 100. This is only a 5% scale. They're missing everything down here from 0 to 95. So it makes the comparison, it makes the difference look larger than what it actually is. So, now, a quick summary. What did we cover in this particular lecture? The first thing was that there were different scales of measurements. If you remember, there was the nominal, there was the ordinal, and there was the numerical. And what's the difference between them? The nominal and the ordinal are similar in the sense that their data are categorical, and most of their data tend to be qualitative, meaning there is some kind of human factor or human subjectivity involved in their measurement. Now, in comparison, numerical data is physical measurements, meaning that's very objective. There's no human factor involved, and it will be stuff like height and weight, for example, where there's no argument in terms of human biasness. Now, the difference between nominal data and ordinal data, it's in terms of order. Ordinal data tend to have inherent order inside them. There's the different groups there maybe go from smallest to biggest. All right. Numerical data has two kinds as well. There's the continuous type data, where there's infinite precision, as well as the discrete type data, where the data inside there is inherently integers, meaning there's no they're round numbers. There's no decimal points into them. Then we talked about, after having all these different measurement types, after we collected them, how then to present them. The take-home message I just want to bring up here is that I personally, now this may differ for other people, but I personally prefer tables, frequency tables, contingency tables for most data, and for numerical data I prefer box plots and scatter plots. Right? All other graphical methods I feel are kind of inferior to these two simple methods of tables and box plots. And we showed a couple of examples of what not to do when you have graphs and you have tables. Now, I should say that designing good graphs and good tables are largely and is largely an art, and something that it's not so much learn as as the more you do, the more you recognize when you're making mistakes and when you're making actually good presentations of graphs and tables. With that, I'll see you in the next lecture.